Hello, my most wonderful AP students. Yes, even a teacher can be a suck up sometimes. And let me get my pen here. And today we're going to talk about the Krebs cycle, also known as the citric acid cycle. Now, when we left off from glycolysis, we had a pyruvate. And that was on its way to the mitochondria. Remember, that is in the cytosol. And so then we have our mitochondria. And remember, we have the cristae side, double membrane. And in order for the pyruvate to get inside here, there is a transport protein. So the pyruvate comes here, but before it, remember this is 3 carbon molecule. But before it can get in there, it needs to lose a carbon. So you're going to be losing a CO2, and you have a thing called coenzyme A. And what's going to happen as this goes in here, it's kind of like when you come to a house, you come to your house, somebody's house, and you want to get in the door, but they say, take off your shoes before coming inside. So we have 2 pyruvate, and both pyruvates have to lose a CO2. And as they lose the CO2, the acetyl-CoA will bind, and it will become what we call acetyl-CoA. And that's 2 carbons. And once it's inside, it's ready to start doing the Krebs cycle. So we have the acetyl-CoA, two carbons, and then we have, now you don't need to know the names of all the intermediaries, all the different things, but I do feel it's good to know the beginning of the first intermediate, the first molecule that's going to bind to the acetyl-CoA, and that is oxaloacetate. And that just happens to be a 4-carbon molecule. That's going to come here, and acetyl-CoA is going to join it, and we're going to get a 6-carbon, no, I wanted yellow, a 6-carbon molecule that is known as citrate. Now, why I want you to know that one is because citrate is also known as citric acid. So citric acid or citrate is the first product produced by the Krebs cycle or the citric acid cycle. Now, as this continues, there's 8 steps. 8 steps for the whole thing. You don't need to know the steps. And 5 steps produce either NADH, FADH2, which is another proton carrier, or ATP. Actually, when you get through and you recycle the oxaloacetate, you will end up having 3 NADHs. This is for 1 pyruvate. You will end up having 1 FADH2 and 1 ATP. But that means if it was an entire glucose, it would be 2 times all of this, meaning 6 NADHs, 2 FADH2s, and 2 ATPs. And usually what we're doing for this is we're following the entire glucose molecule breaking down, not one pyruvate. And all these will result, all these except for ATP. Now, one thing you remember that when you have an ATP here, it is what we call substrate phosphorylation, meaning it's an enzyme that's putting it together that just binds it, that takes the ADP and a phosphate and puts them together, where the other ones will be what we call chemiosmosis, in other words, using the ATP synthase and the electron transport chain producing the hydrogens that are used there. So these all will result in ATPs via the electron transport chain. Now that's basically Krebs cycle in a nutshell. You don't, like I say, you don't have to know the enzymes, except for when we hit the electron transport chain. The enzyme here would be a carboxylase, meaning it's adding a carbon to something, just like Rubisco in the Kelvin cycle. But these 3 things I feel it is good to know: acetyl-CoA, oxaloacetate, and citrate or citric acid. So that's because that's the start of it, and that's where you have the name. So, but the rest, is just that it's 8 steps, and it's a cycle that'll keep on recycling the oxaloacetate back into citric acid as long as we keep on having acetyl-CoA coming and pyruvate being made. Of course, if ATP builds up, then you're going to have, it will shut this down because you're not producing pyruvate, because you are inhibiting the phosphofructokinase back in glycolysis. Now, let's go to your, okay, here's a very simple thing here. Here we have our pyruvate. It comes in here. We have a transport protein. CO2 is released, and we end up with, as it comes in, where it looks here, the CO2, it looks like the CO2 is being released in the mitochondrion, but the CO2 is released before it is allowed in. Like I said, you take your shoes off before you come into my house. Not really, but some people's houses. And you got acetyl-CoA. And the one thing I didn't mention is that when you do, from this, we call this pyruvic oxidation, you do get an NADH. So for 2 pyruvates, you'll have 2 NADHs. So that also, once again, will add up to the number of ATPs that you get once we go to the electron transport chain. Now, real quick, citric acid cycle, also called the Krebs cycle, takes place in the mitochondrial matrix inside. The cycle oxidizes organic fuel derived from pyruvate, generating 1 ATP, 3 NADHs, and 1 FDH2 per turn. So for glucose, it's 2. But remember that, as I just said, the pyruvate, as it goes to acetyl-CoA, we get another NADH, because that's not actually part of the cycle. And here we have it. And so pyruvate. And here it's showing that this CoA comes in, the CO2 is off before the coenzyme A is inside, but that CO2 is released before that coenzyme A comes on there. And there's lots of enzymes. Basically, you can say there's 8 steps, and so there's an enzyme in every step. And it says 3 NADHs here, well, actually, they're not all converted. They're actually 1 NADH, 2 NADH, then ATP, then the FAD, 2 FADH2, and then you'd have your final NADHs up there. So they're not all occurring on time. This is just a simple diagram, but once again, you don't have to know all that. Okay, has 8 steps, each catalyzed by a specific enzyme. Okay, acetyl group, acetyl-CoA joins the cycle by combining with oxaloacetate, forming citrate or citric acid. Next 7 steps will decompose, meaning breaking down the citrate back to oxaloacetate. So you see, you're only losing 2 carbons. So you're only only losing the 2 carbons from acetyl-CoA. That means what you have to understand, you're making different isomers, and some of these isomers become lower in energy, which means that it's releasing energy to be able to either transfer an electron to NADH or FAD to NAD plus or FAD2 plus, or to be used to phosphorylate an ADP. And finally, as I said, we end up with the NADH in these, and they'll be used. They're electron carriers, and they take them to electron transport chain, and there it'll be used much like it was used in the photosystem 2 to pump protons in. That will be used for chemoosmosis. In other words, for using ATP synthase to produce more ATP. And that's it. I'll make another short video on electron transport chain.